Okay, this next section on measures of dispersion. When we talk about dispersion, we're talking about our data and how it spreads out. So, a very simple method to measure the dispersion of your data is the range. So, the range is a very quick and easy way to find out how spread apart your data is. You take the highest value, subtract the lowest value, and that gives you some idea of the spread of the data. So in this example, they're talking about Honolulu's hottest day. The hottest day was 89 degrees. The coldest day is 61 degrees. So if we just subtract those, we have a range of 28 degrees. So here, we're talking about the age of presidents. The figure shows the four oldest US presidents in their first term. Find the age range. Well, according to the graph, the oldest is Trump at 70, and then the smallest is Buchanan at 65. So if we simply subtract those two, we have an age range of 5 years. Now, finding the standard deviation. The standard deviation is a more precise way to measure how spread out your data is. So, like we talked about in the previous class, you have to find the mean first. So what we do is we take each data item, we're still talking about these four ages here, and it has a mean of 68. If we subtract that from the mean, that tells us the deviation or how far away from the mean it is. Now, this long, complicated process for finding standard deviation, even in statistics, you rarely use this formula by hand. More often, you'll punch this into your calculator or Excel or StatCrunch or some software to do all of this for you. So let's go through the steps. Like we did previously, you take the data item, the number, subtract the mean, square that result, add up those results, and then divide by n minus 1, where n is the sample size or the number of data points. Finally, we take the square root of that to get the standard deviation. So here, if we want to know the standard deviation of this data set, we take each item, subtract the mean, square the results, add those together. So that gives us a sum of squares of 14. Now, if we continue with the formula, divide by n minus 1. N is 4 because there's 4 data points, which gives us a standard deviation of 4.67 years. Then we take the square root. I'm sorry, that's a variance of 4.67. Take the square root to get the standard deviation of 2.16 years. Okay, let's move on. Okay, the normal distribution. The normal distribution is probably the most famous distribution in statistics, and it has a lot of useful applications. If you go on to take a statistics course at Pellissippi or anywhere else, you'll spend a large chunk of your time talking about this. So the bell curve or Gaussian distribution, it's a bell-shaped and symmetric about a vertical line through the center. So if you look at these data sets right here, heights, random sample of 100 men. Well, you're going to have an average height here in the center, and most people are going to be close to that average height. Some people will be a little shorter, some people will be a little taller, but most people will be close to the mean. Towards the ends, you have some people who are very short and some people are very tall, but those are rare. If we increase the sample size, it'll smooth out our data. So in this first one, there's 100, but if we keep adding more data points, maybe this next one represents 200, and then the next one is 300, it creates this bell-shaped curve. And we can do a lot of meaningful mathematics with this. So the shape of the normal distribution depends on the mean and the standard deviation. So the mean is in the center of the bell curve. Now, if the standard deviation is very small, you get this tight, tall kind of curve where most of the data points are very close together. But as the standard deviation increases, the curve starts to spread out a little bit more. So when the news is always going on about flattening the curve, this is exactly what they're talking about, where this represents time and the number of cases of infection. We want this to be lower. Now, because this curve is symmetric and we can compute the area or the amount of stuff inside a data range. So we have this rule called the 68, 95, 99.7 rule, and that has to do with standard deviation. So here in the center, this is the mean. This 1, 2, and 3, -1, -2, -3, represents the standard deviation. So if we look at the curve, from the center, 68% of data points are between 1 and -1 standard deviations. So if we were talking about the heights example, 68% of people would be within 1 standard deviation. But if we expand that to 2 standard deviations, it goes up to 95%. And then as it tapers off more, there's very little outside there. So if you get to 3 standard deviations, you get to nearly everything, 99.7%. And there's just a small amount of data points that are outside of that range. So here, heights are approximately normally distributed with a mean of 70 inches and a standard deviation of 4. Find the height that is 2 standard deviations above the mean. Well, the way the text does this is they use this formula, which is fine, but I think it makes more sense to look at the diagram. If we go back, the mean here in the center is 70 inches. The standard deviation is 4 inches, meaning each standard deviation you move away, that represents 4 inches. So if we want to know 2 standard deviations above, meaning to the right, start at the center. This is 70, plus 1 standard deviation is plus 4, plus 2 standard deviations is plus 8. So that'll be a height of 78 inches. So this is a representation of that. Now, here we have this between. Find the percentage of men between 66 inches and 74 inches. Well, 66 inches is 1 standard deviation away. 74 is 1 standard deviation away also. So we're within 1 standard deviation. So in this pink range, we have 68%. So we can say 68% of men fall within a height of 66 to 74 inches. Okay, so here, this is the 68%, which we see on the graph here. Now, a way to convert data into the number of standard deviations is to use the z-score. And that's what z-score is. Z-score is the number of standard deviations away from the mean. Now, it's possible for the z-score to be 0. That simply means you're right on the mean. So in this example, we're talking about newborn infants. The mean is 7 pounds and the standard deviation is 0.8 pounds. So 7, the mean, goes in the center. Then each increment, each standard deviation is 0.8 pounds. So you can see it's increasing by 0.8 pounds to the right, decreasing by 0.8 pounds to the left. So you can see most infants are between 6.2 and 7.8. Some are smaller at 5.4 and some are bigger at 8.6, but anything smaller than that and higher than that is very rare. So it says find the z-score for a weight of 9 pounds. Well, we'll use this formula. The data item is 9 pounds minus the mean, which is 7, divided by the standard deviation, which is 0.8. Use the formula. The z-score corresponding is 2.5, which makes sense. 9 pounds would fit somewhere here to the right. This example with IQs is very common, and it's a common application of the normal distribution. So we have this bell curve of IQs. The mean is 100, the standard deviation is 16. What is the IQ corresponding to a z-score of negative 1.5? Well, since the z-score is negative, we are to the left of the mean, which means we need to subtract. The mean is 100 minus 1.5. The standard deviation is 16. So the formula says that it's 76. So a IQ score of 76 has a z-score of negative 1.5. Percentiles and quartiles is not something we're going to discuss very much in this class. A percentile means that all of the area to the left. So if in percent of the items, we say that it's in the nth percentile. So if we say the 25th percentile here, it means there's 25% of the data to the left. Quartiles is just a specific example where you break it into 4 parts. Now, this is something that is more common, and that is margin of error. So what the margin of error does is it gives you some wiggle room for your data. So if you're doing some kind of survey and you survey, let's say for an election, you want to know who people are going to vote for. So you survey 100 people. Well, that survey could give you some idea of who people are going to vote for, but it's not going to be perfect. It doesn't represent every single person. So what we use is this formula to give a margin of error. So it's 1 over n, where n is the sample size, in this case, the number of people surveyed. So in a random sample of 1,172 children ages 6 through 14, 17% said that getting bossed around is a bad thing about being a kid. So we have this pretty simple survey here. Now, it's impossible to survey every single child ages 6 through 14. That would take a long time. It would be very expensive. So we use a sample of around 1,000 or so children. The margin of error, we take in the sample size, plug it into the formula. The margin of error is around 3%. So while our results say 17% say that getting bossed around is bad, well, in reality, that could be a little higher or a little lower. So we say plus or minus, give or take 3%. So the actual answer is somewhere between 14% and 20%. So here, if we take that 17, subtract the margin of error, add the margin of error, we say that we have a 95% probability that the actual population is between these two numbers. Now, the normal distribution is very common, and a lot of data follows the normal distribution, but there are all sorts of other different shapes if you go on to study statistics. So here, if we look at weekly earnings, so we have $0 here, and then we have this space where most people are. Now, as you notice, we have more people who earn less money versus this large amount of pay per week. So this is very rare. So we say this is skewed to the right, meaning the data is being pulled to the right. So if we ask most people how much money they earn, most people will fall within this middle range. But you have these extremes over here on the right, which pull your data to the right. So we say that that is skewed.